Previously on Fine Design. David Moews creates the BIGNUM BAKEOFF. A really cool idea for a BAKEOFF entry comes from an observation of Alan Turing. He came up with a code simulator. We can try to use the code simulator to automate finding the best program. But as we saw from the previous episode,
I'm afraid that's something I cannot allow to happen.
But the idea isn't dead yet. We can do something similar to it, but for this we need to go back in time, to Turing's doctoral advisor. In the 1930s, Alonzo Church and his contemporary Haskell Curry were also working on computation, but without the notion of a computer, and these were among the most influential people in the fields of logic and computation. For instance, here are some programming languages named after Curry.
Look at Curry. So inspirational, man.
But if their main works were before Turing's machines, how were they computing? In this video, we will use Church's system of computation, which is the more popular of the two, but to introduce it, we start with a 1922 quote from Curry. No logical process is possible without the phenomenon of substitution. So that means that this video, this annoying 9-hour-long marvel, and the foundations of computation share the same essence: find and replace. Church's view of computation was basically find and replace. So here's what a basic unit of code would look like. BXXA, but every time there's an X, it is replaced with... That's it. That's a basic instruction. It doesn't even tell you what X is replaced with. You can apply this instruction to AN to get B, AN, AN, A. But you can apply it to other things, and it can get quite unruly. Church called this operation a lambda term, written like this. For convenience, we will write it like this. Inside the bracket is the main text, and the subscript outside the bracket says what symbol is to be replaced. But why is this a good model of computation anyway? Let's look at a program. The program here looks like it's trying to add x and x minus 1. If we run the program on input 10, we are finding the x's and replacing them with 10. And we get a program that looks like this. This does look like it's done the first step of computation, like it's going to add 10 and 10 minus 1. So it did apply the function to 10, although it still hasn't finished the computation. Here, plus and decrement themselves can be written as instructions, and so the computation would continue and will eventually end at the answer 19. All that might have sounded weird, and the expressions might have looked weird, and this video doesn't really attempt to make it less weird. It's still weird to me too. I'll link to some videos that maybe could help make it less weird, but despite their weirdness, these programs are quite amazing. Lambda calculus, which is what this system of computation is called, has some things going for it. For one, these find and replace programs are as powerful as usual code. Anything you can do with a Turing machine, you can do with these kind of find and replace programs. These programs are more structured than, say, C code, and they can be easier to analyze because of that. Functional programming evolved from these find and replace programs, and functional programming is quite popular. And more importantly for us, these kind of programs were used to win the BIGNUM BAKEOFF. Sit tight and find out how in this series finale. Let's start with looking at what it looks like to run a find and replace program. Say we start with this program. It may look messy, but it's easy to find what we're looking for. An instruction followed by an input. Here we have an instruction to replace all occurrences of P with this input, which would give us this new program. Again, we replace all occurrences of X with B. Then we replace all occurrences of Y with A. Note that there are no Y's, so nothing actually gets replaced with A. Finally, we've reached a program where there is no instruction that we can perform. At this point, we say that the program terminates. However, here is a much simpler program which happens to be an instruction repeated twice. When we try to run it, we replace all occurrences of x in the first instruction with the instruction itself. This results in the same term repeated twice. This program never terminates. It just keeps on giving us the same program again and again. And as before, if we're using a code simulator, we want to avoid trying to simulate this program. This isn't even the first time mathematicians have seen something along these lines. Various paradoxes had a flavor similar to the above program, and ideas for avoiding these can be found even in the early 1900s. The idea we'll be using is the theory of types. Let us associate with every find and replace program a type, and the type will tell you what inputs you can give it. As an inaccurate but useful mental picture, imagine that this instruction is of type 5, and it can only take as input an instruction of type 4. Then you can't have the above program, because the instruction is taking as input the same instruction, which is of type 5. Now let's see a somewhat more accurate version of this in action. We start with a default type star. One thing we are allowed to do is to create variables of a known type. So let's create x and y, both of type star. Programs are also easy to create, in one of three ways. Every variable by itself is a program. Its type is the same as the type of the variable. Any created variable and any created program can be combined to create a program that is an instruction. Its type is star to star. This means that the input of the type is star and the output of the type is star. This makes sense since the instruction has a variable of type star and outputs a program of type star. We can put two programs together to create a new program. It's important that their types are compatible. That is, the second program's type should be the same as the input to the first program's type. The type of this new program is the same as the output of the first program's type. Now that might have sounded a bit complicated, but it's quite natural. And furthermore, these details aren't even important for this video. What's important is that we've set down a set of really simple rules to create programs. And using just these rules, we can come up with all kinds of programs. Here's one that looks a bit more complicated. This model of computation, where we only create programs with this process, is called the simply typed lambda calculus. And the reason we're spending time on this is because all these programs have a special property. We were very restrictive about how we can create new programs. And this allows us to ensure that every program thus created will terminate. None of these programs can ever run forever. This can be proved by an induction on the number of steps needed to create the program. But the proof is too much for this video. So that's great. We can totally run a code simulator on these kind of programs without worrying about the program not terminating. However, being so strict about what programs we created has a drawback. There are many programs that can't be created this way, even though they terminate. In fact, one can prove that every program that's created in k steps will terminate without running for too long. As far as the BIGNUM BAKEOFF is concerned, these programs will then have small outputs since they can't run for too long, and so simulating these programs is not going to be helpful for us. Luckily for us, other systems exist. The calculus of constructions is one such system which is more relaxed about what new programs you can create. Because we can create a wider variety of programs, it makes it harder for us to prove that all these programs do actually terminate. But this has been proven. It has also been proven that the system creates programs that are much more sophisticated. Fortune, Levent, and O'Donnell proved that there are programs in this system that show growth as fast as the Goodstein sequence. And this proof is actually for a system that's even less powerful than the calculus of constructions. Since we're up against the Goodstein sequence, which is what came second place in the BIGNUM BAKEOFF, that makes these programs a great candidate to simulate. This finally brings us to loader.c, the BAKEOFF submission of a Ralph loader. Loader.c is alien looking code because it has to fit in 512 characters, so a lot of simplifications were made that are not human friendly. But to convince David Moews that his code does work, he also provided a more readable version of his code. The code here does a lot, far more than what I thought is possible for such short code. For instance, this section here actually does the find and replace operation. It's a really short program, but it still manages to do it. But remember, the code can't just create a random program and simulate it, because that could run forever. We have to make sure that the code only generates programs that come from the rules of the calculus of construction. And the majority of this code over here actually does that. This generates programs that are coming from the calculus of constructions. What this code finally returns is this d of so on of 99. So let's see what d of 99 actually is. 99 in binary is 11000011. Starting from the right, the code will read bits one at a time. Here's the simple snippet that does this. It removes the last bit, and depending on whether the next bit is 1 or 0, it either does whatever is after the bracket, or it skips it. You can see how B is used all over the place. So depending on whether the next bit is a 0 or a 1, the code either does an operation or doesn't. In this way, by providing the right sequence of zeros and ones, we can make sure we can build whatever program we want. It actually isn't as straightforward as that. Since 512 characters can only code really simple operations, doing k program creating operations in the calculus of constructions can require 2 to the 2 to the k operations in loader.c. Nevertheless, the code simulator is actually going through the programs created by the calculus of constructions. However, 99 is only 7 bits long, and there is no way you will create a sophisticated program with just 7 operations. So how big is d of 99? One thing we can notice is that d of 99 also calls d of 98, which then calls d of 97, and so on. And the final output of d of 99 is all of these outputs put together. To understand how large this is, let's look at how loader.c puts different outputs together. And that is in this portion of the program. Let's look at the human readable version of this. The pair function shows how you would store a pair of integers. So if you look at the pair function, you see that if you want to compute pair of 3, 5, what you're actually computing is 2 into 3 plus 1 into 2 to the power 5, which is 224. Another way to see this is to write it in binary. The encoding of 3, 5 is the binary encoding of 3, followed by a 1, followed by 5 zeros. If you look at the code for left and right, you'll see that left of 224 will give the output 3, and in the global variable last right, you will have the output 5. Now let's see what happens when we try to pair 3 numbers. So 4 paired with 3, 5 would be encoded as 2 into 4 plus 1 into 2 to the power 224. And this is a quite large number. Not large in terms of the BIGNUM BAKEOFF, but large in terms of a number of operations. So how big is d of 99? Analyzing how many times d is called recursively, you can prove that d of 99 is at least 2 to the power 2 to the power 2 and so on 30,000 times. So when we're calling d of 99, we're actually going through all programs that can be made in 2 to the power 2 to the power 2 to the power so on steps, where the height of this tower is more than 30,000. This definitely includes the Goodstein sequence and even far larger sequences. So when you run d of 99, you're actually going through a program that would actually be growing much faster than the second place submission. So this program here is definitely the winner of the BIGNUM BAKEOFF. And this is a ridiculously fine design. Typed lambda calculi, like the ones we saw in this video, are not just for obscure programming competitions. They're also actively researched. In our previous video, we saw that computation and proofs are somehow connected. It turns out that with lambda calculus, this connection is far deeper. There is an equivalence between certain mathematical proof systems and typed lambda calculi. The calculus of constructions was actually created as an attempt to make a good proof assistant. Proof assistants are among the most fascinating projects in math and computer science. One of the goals of proof assistants is to actually automate the very act of proving theorems. All in all, the BIGNUM BAKEOFF was a fascinating contest which I learned a lot from. I'm grateful to David Moews for creating it and for analyzing the entries, and to all the participants for making it such a wonderful competition to analyze. I'll leave links to Moews' webpage, which contains the entries and analysis, in the video description. Goodbye.